How far back would you have to pull an ordinary rubber band in order to launch it into space? Well, let's do the math. We'll start by calculating escape velocity. Escape velocity is the speed an object must be going in order to make it into orbit. As any object travels up through the atmosphere, it loses kinetic energy and gains potential energy. The total change in energy is zero, however, because energy cannot be created or destroyed. So kinetic energy, 1/2 mv squared, must equal potential energy, big G big M little m over r. We can rearrange this equation to get V equals the square root of 2 big G big M over r. Big G is the universal gravity constant, 6.67 times 10 to the negative 11th. Big M is the mass of the Earth, or 6 times 10 to the 24th kilograms. R is the radius of the Earth, or 6.4 times 10 to the 6th meters. Plug these in, and we get that escape velocity is 11,200 meters per second. Now we need to find how far our rubber band will have to be stretched. Since we know that impulse is both m delta v and f delta t, we can use the equation m delta v equals f delta t. We also know that f equals kx and delta t equals pi square root m over k. If we put all these together, we get m delta v equals kx pi square root m over k. Rearrange to solve for x, the distance pulled back, and we get the monstrous equation x equals m delta v over k pi square root m over k. Now this may look difficult, but it's really not that bad. M is the mass of the rubber band, about 0.00025 kilograms. Delta v is the change in velocity when released, which needs to be escape velocity. Earlier, we calculated this to be 11,200 meters per second. K is the spring constant of the rubber band, which is on average about 88. Using all these values, we get our final answer of 6.1 meters, or 20 feet.